start 3.5. It's a long section. There's a lot of content in it. So we're going to start today. We'll finish it up on Monday. Okay? Introduction to functions. There's going to be a lot of similarities from what we've been doing with linear equations. We're just adding onto it and adding some specificity with the functions. So, starting with our ordered pair. That is mine. Starting with our ordered pair, x and y. X is our independent variable, y is our dependent variable, meaning y depends on x, okay? We determine what y is, or we determine what x is, we put in values for x, we evaluate our function, and we get an output of y for our ordered pair. All of our equations, our graphs, our tables, sets of ordered pairs, they'll all be relations. What we have to do is then use some specific values to determine which of those relations are specifically functions. But a relation is just a set of ordered pairs. We're comparing two things. We're comparing some x values to y values, inputs to outputs, independent variables to dependent variables. Okay? But a function is a very specific relation in which each independent variable only corresponds with one dependent variable. Meaning, whenever we plug in a value for x, we will only get one value for y. Okay? So that it's consistently the same output with every single input that we use. So when we're looking at a list of ordered pairs, to determine whether it's a function or not, you want to see do your x values repeat. If your x values repeat and give you a different y value, then you're not going to have a function. But if all of your x values are unique, then you have a function.
How do we determine it?
So you look at your x values. Okay, what are my x values of a?
0 and then -1.
Do any of those numbers repeat?
Yes.
Do they give me different outputs?
Yeah.
Then it's not a function.
What is in the function, that whole A?
That relation is not a function.
Well, that's all we have to do.
When you're looking at a relation, basically yes. Do our x values repeat?
So we just had the same point twice.
If I had -1, 2, and then -1, 2, and then -1, 2, and then -1, 2, every time I plug in -1, it's giving me the same output of 2. So it's a function. Alright? But if I have -1 and it gives me two different values when I plug it in, or 3 or 4 or 5, then it's not a function. Looking at letter B, what are my x values? Do any of those so that it's a function?
Wait, what? They don't.
Right. They don't repeat, meaning it's a function. Every x value corresponds with only one y value. Now, in this case, my y values repeat, but that's fine. I can point to the same y value with different x values. I just can't repeat. I like to use this analogy. Okay? Test scores. Alright? You take a test, and Sean and Ella both get 90s on their test. That's okay. Two different students, x values, got the same test score. That's fine. It's allowed. What I can't have is one student, Sydney, getting a 90 and an 80 on the same test. Because it should be like, well, which one did I get? Was it the 80 or the 90? So it's not a function with one student getting two different test scores on the same test. It is a function if I have two different students with the same test score. Okay? So do your x values repeat? If they do, and you get different outputs, not a function. If they don't, then it's a function, regardless of what the y values are. Okay? What your y values are has very little determination of whether or not it's a function, as long as your x values don't repeat.
So even if the -1 with the 2 on it was a 3,
If it gives you the same value, it is a function. If I had -1, 3, -1, 3, -1, 3, then that is a function because every time of -1, my output is 3. It's giving me the same output. Different outputs. Is it a problem? So, Sydney gets a 90 on her test. And every time she asks me, what did I get on my test? It's a 90. What did I get on that test? It's a 90. Every time. But if every time she asked me, I gave her a different number, then there's a problem. Does that make sense? So she asked me today what she got on her quiz. She said 90, but she asked me tomorrow, and I tell her it's an 80. And she asked me again, and I say it's an 85. And then go. So, make sense? All right. Go for it. Okay. So, this is just another way of showing a relation. Okay, these are called mapping diagrams. And so we have input and we have output. And so in this first map, I have 1 is my input, and it points to 2 as the output. Okay, so I put in 1 and I get out a 2. Or I put in a 2, I don't know why it's not swiping. I put in a 2, I get out a 5. I put in a 3, I get out a 6. Okay, so for each input, it only corresponds to 1 output. So I have a function. But if I go to my next map, I take 1 and it points to 2. That's good. X only corresponds, this value only corresponds to 1 output. But 2 corresponds to 2 different outputs. Okay, not a function. If I represented these as ordered pairs, it would be like having 1, 2, 2, 5, and 3, 6, all a function. None of my x values repeat. But here, I have 1, 2, then I have 2, 2, and I have 2, 6. X values repeat. They give me different output values, not a function. Same idea, just different representation. Mapping diagram versus ordered pairs. Okay, all right. The fact that 1 and 2 both point to 2 is fine. What's not okay is that 2 points to 2 at 6. Now, domain and range. Domain represents all of the possible x values. Range represents all of the possible y values of my relation. Okay? We have 3 different ways that we can represent domain and range. Set notation, interval notation, inequalities. Okay? And we're going to go over all of those. Set notation is used when we have a list. Set notation is for when we have a list of numbers. If I have a list of numbers, I have a set, I have a bunch of just ordered pairs, or I have just a set of points on a graph, or I have a table of values. It is a list of numbers. I'm going to use set notation. Okay? So domain represents all of my x values. Okay? Which are my input or my independent variable. Okay? Independent variable, the input, the x values. Looking at this table, if I have a year, and then based on each year, I know how many cell phone subscribers I had, which of those values is my independent variable? Okay? Because I can look at a year, and then I say, okay, for that year, how many subscribers did I have? The subscribers depends on the year. Okay? So year is my independent, and then subscribers is dependent. So x and y. Okay? 99 times out of 100, year is always going to be the x value. Okay? There's very, very few cases where time is our y value. Okay? Rate of decay is usually kind of the only time that you might switch. But 99 times out of 100, year is our independent variable. Okay? Now, domain is going to be each of those years. The year 1990, the year 2000, 2001, 2002, 2003, 2004. So I'm going to list those out. Set notation uses curly brackets. Okay? Curly brackets is for set notations. The only time we use it is when I am listing numbers. So I will list those numbers. 2, I'm running out of room, 2004. Okay? So set notation, I'm listing those specific numbers for my domain. Then range, I'll list all of my subscribers. Same thing, set notation. Okay? I'm really bad at drawing curly brackets. I drew a really good one earlier today, and I just can't do it again. Okay? And then I would just continue listing those numbers. I don't feel like listing out all those numbers. Okay? So I would just list all the numbers and enclose it into curly brackets. That is the set notation, and we only use it when I'm listing specific numbers. Okay? Our other two notations, interval and inequality, are for when I have a spread of numbers. Okay? I have a continuum of values. Okay? Or a range. I don't like saying range because we're using range, but I have a range of ranges. So when I have this continuum of continuous numbers, I'm going to be using my other two notations. But with a list, it's going to be set notation. All right? In curly brackets. All right? So we're not going to use set notation on a graph, on a continuous graph, because I have an infinite number of points. All right? I have -2, -1, 0, 1, and 2, and it keeps going forever. And I also have all the numbers in between. I have 1/2. I have -3.4. I have 5.7 repeating. I have an infinite number of values, so I can't just list out all the numbers. All right? So I have to indicate that it is a continuous set of numbers. So we're still looking at domain. And then looking at the graph on the domain, I'm focused just on the x-axis to start. Okay? And my line continues down and to the left forever. Okay? So what do I use to indicate left forever? Negative infinity. Okay? And this is going to be our interval notation. Interval notation. We're going to start at negative infinity. We always start with the lowest value, okay, towards the negative side. It doesn't mean you're starting with a negative number. Just starting on the lowest side. Now, since it goes forever to negative, then we have negative infinity. And then I come here and I'm going up, and then I keep going down into the right forever. So what represents right forever? Positive infinity. And then instead of using curly brackets, we use parentheses. Okay? Parentheses on infinity. Parentheses always on infinity. Okay? So that's interval notation. Come back with another one. Range. Actually, let me use a different color. Range. Okay, again, I'm going to use interval notation. And I'm going to start the lowest end. Okay? What's the lowest possible y value if my graph goes down forever? Negative infinity. Okay? Now, got that parentheses. Okay? But does my graph go up forever? No. Where does it stop? 4. Okay? Bracket. Man, you guys are smart. Okay? That 4 is included. Interval notation. Now, the other way we have it is as an inequality. Okay? Inequality. Okay? Inequality uses the greater than symbol, the less than symbol, greater than or equal to, less than or equal to. Now when I have negative infinity to infinity, I can't use an inequality because it's everything. I don't have a value where it starts or stops. So for inequality, we just write all real numbers. All real numbers for negative infinity to positive infinity. Most of our functions will have a domain of all real numbers. Not all of them, but most of them. Range is where it varies. Okay? Sometimes we'll have a range of all real numbers. Sometimes we won't. Just depends on the graph. Okay? So I have a range of negative infinity to 4. All right? And so I have all values less than or equal to 4. And range talks about my x or my y. The y. So when I'm writing an inequality, I'm going to say that y is all values less than or equal to 4. Okay? So, interval notation, inequality. You need to pay attention to how they want it. Most of the time I use interval notation. But sometimes inequalities show up. So you need to be aware of that and pay attention to that. All right? And this is the last thing I want to talk about here is, again, determining whether or not a graph is a function. So we can look at domain, we can look at range, we want to determine if the graph is a function or not. So we look for, does an x value repeat? Okay? Does an x value repeat? And if it does it give me a different y value? Graphically, we use the vertical line test, but it's testing the same thing. Does an x value repeat? If I draw a vertical line anywhere and everywhere through this graph, I'm only going to get one output for every single x value. It's only ever going to touch at one point at a time. And as long as it only ever touches once, and that means no, the x values don't repeat, and it is a function. It passes the vertical line test. If it only ever touches once, it passes the vertical line test, and I have a function. But if I draw a vertical line and it touches more than once, that means the x value repeats. And it fails the vertical line test and is not a function. Okay? So if I'm given a list of ordered pairs, if the x value repeats and gives me different y values, not a function. If I'm given a graph, vertical line test, does it pass more than once? Function. Okay? If it passes the vertical line test, then it's a function. If it fails the vertical line test, then it's not a function. All right? On Monday, what we're going to do is we're going to look at equations, and we're going to see a pattern with certain equations, and we'll kind of see something that recognizes where I don't have to see the graph. If I know what the equation looks like, there's a certain set that kind of allows us to know whether it's going to be a function or not. But we're going to do that on Monday.